Let's look at an example of case 2 where we have real and repeated roots. So in this example, we want to find the inverse Laplace transform of this function f of s, which is 100 times the quantity s plus 25 divided by s times the quantity of s plus 5 cubed. And so what we can do is we can write this out in terms of our residues k and our different partial fractions. So we have an s plus 5. We're going to have, we can call this k1 to be consistent with our terminology from the previous video. We're also going to have an s plus 5 squared in the denominator, so that's going to be k2. And we need to go all the way up to k3 divided by s plus 5 cubed. And so that's because we had s plus 5 cubed in our initial equation. And then we also have this s term in the denominator, so we have to have an additional coefficient for that, so that's going to be k4 over s. So now we just need to solve for our values k1 through k4. So our values k3 and k4 we're going to find the same way that we did for case 1. So let's first look at finding k3. So finding k3, we're just going to take this f of s, so let me just copy this here. So we're going to copy our f of s, and we're going to multiply that by our s plus 5 cubed. So we're multiplying by s plus 5 cubed, and after doing that, we're evaluating at s equals negative 5. And so, of course, what we can see here is that our s plus 5 cubed is going to be canceling out, and what we're going to have over here is on the other side, we're also multiplying by this s plus 5 cubed. So what we're going to end up having is we'll have s plus 5 squared times k1 evaluated at s equals negative 5 plus s plus 5 times k2 also evaluated at s equals negative 5 plus k3 and plus s plus 5 cubed over s times k4 evaluated at s equals negative 5. And so what we can see on this right side over here is any of these terms with the s plus 5 still there are going to go to 0 because we're evaluating at s equals negative 5. And so all that leaves is this k3 term. So we have that our k3 is equal to what's left on our left side evaluated at negative 5. So we have k3 is equal to 100 times negative 5 plus 25 is going to give us 20, and negative 5 in the denominator. So evaluating that, we get that our k3 is negative 400. So again, same way as what we saw with our case 1 of real and distinct roots. Same thing for our k4. Because there are no repeated roots at s equals 0, we can do the same thing that we did for case 1 here as well. So let's say we're finding k4 now. And so what that's going to look like is, again, we're just going to be multiplying our f of s by s in this case and evaluating at s equals 0. All of our other terms we're also multiplying by s, so we have s times k1 over s plus 5 evaluated at s equals 0 plus s times k2 divided by s plus 5 squared evaluated at s equals 0 plus s times k3 divided by s plus 5 cubed evaluated at s equals 0, and then plus k4 because that multiplying by s is going to cancel out with the s in the denominator. So again, we can see that on the left side these s's are going to cancel out, and on the right side anything with an s in the numerator is going to be going to 0. So that's these first three terms, and we're just left with our k4 on the right side. So plugging in values, we have k4 is equal to 100 times 0 plus 25, which is just 25, divided by 0 plus 5 cubed, which is just 5 cubed. So evaluating that, we see that our k4 is equal to 20. Okay, so now where we're deviating from our case 1, we need to find our k2 and eventually our k1 as well. So for this k2, let's sort of step through the process, and then for k1 we'll come back and we'll use our generalized equation. So remember, what we're going to do is we're going to multiply both sides by that s plus 5 cubed. So multiply both sides by our s plus 5 cubed. Then we're going to differentiate both sides. Okay, so what that's going to look like is we're going to have derivative, and let me give myself as much space as possible here. So we're going to have derivative with respect to s of, and now if we've multiplied our f of s by this s plus 5 cubed, we're essentially looking at this equation here, the same right and left side as we have here. We're just going to be taking the derivative of this. So what we have then is on the left, derivative of 100 times s plus 25 divided by s, because we've already canceled out that s plus 5 cubed. And so we're going to be evaluating at s equals -5 after we take the derivative. And that's going to be equal to, so we don't necessarily need to write this out each time, but just for clarity, I'm going to show it to you this time. But we have the derivative of everything on the right side. So on the right side, after multiplying through, again, we're multiplying through by this s plus 5 cubed, we're going to have s plus 5 squared times k1 plus s plus 5 times k2 plus k3 plus s plus 5 cubed over s times k4. And again, after taking that derivative, we're going to evaluate this at s equals -5, same as on the left side. And so again, I'm going to show a lot more detail here than you would normally need to do. But taking the derivative on the left side, we have an s in the numerator and the denominator, so I'm going to use my quotient rule. So low d high minus high d low over low low. So low is just s. Our high, or d high rather, is going to be 100 minus high d low, so our high is 100 times s plus 25, and our low is, our d low is derivative of s, which is just 1, and then divided by low low, so s times s is just s squared. So that's our derivative, and so in the next line we're going to evaluate that then at s equals -5. So let's consider our right side of the equation above. So taking the derivative of that first term, we have the 2 coming down, so 2 times s plus 5 times k1. Taking the derivative of our second term there, we just have k2. Taking the derivative of our k3, we're just going to get 0, because remember k3 is a constant and derivative of a constant is 0. Now for this last term, we're going to have, again, to use our quotient rule, because we have s in the numerator and denominator. So what we get from that is we have our low value of s times derivative of our high, so 3 times s plus 5 cubed, and chain rule, we just get a 1, and then minus high d low, so s plus 5 cubed times derivative of s, which is just 1, divided by low low, so s squared, and we are going to then evaluate, and so that's multiplied by a k4 as well, so let me slip that in here, and we're evaluating all of this at s equals -5 as well. So what we can see is that anything on the right with this s plus 5 is going to be going to 0. So over here we also have s plus 5 here and here, so both of those are 0, so we have 0 minus 0, so this is also going to 0. So the only thing left, as we expect, is k2. So we don't have to go through showing this on the right side each time, but I just wanted to show you this first time just so it can kind of be helpful to see that process. Okay, so we know we're left with just our k2, so we've already taken the derivative of the left. The final thing then is to just evaluate at s equals -5. So we have k2 is equal to, so s is -5 times 100 minus Now we have 100 times negative 5 plus 25, which becomes 20. And in the denominator, we have the quantity of negative 5 squared. So plugging in, we get negative 100 for our K2. Okay, so we found K2, K3, and K4. The last one we want to find is our coefficient K1, or our residue K1. So finding K1. And so in this case, let's look at how we can use our generalized equation. So what I want to ask you then is, in our generalized equation, remember we have some N and we have some M. So take a minute, pause the video, see if you can't figure out, go back, reference the notes, figure out what our N and M should be in this case. So for our N value, we want to come back up here and we look at our initial f of s, and our N is the number of repeated roots we have at that, the number of repeated poles. Roots of the denominator are poles of f of s. So we want to see how many repeated poles we have at that point, and in this case we have 3. So our N is going to be 3. And then our M is determined by what coefficient we're trying to solve for. In this case, we're trying to solve for our coefficient K sub 1. And so we know that this 1 is equal to N minus M, so we know 1 equals N minus M, and if we've already said that our N is 3, then that means that our M has to be 2. So that's how we would determine what our N and M are to plug into that generalized equation. So another thing to note is when we were solving for K2, we have already found the first derivative of interest. So from our previous work, when we were solving for K2, we have already found that our d with respect to s, or our derivative with respect to f of s times s plus 5 cubed can be simplified. So let's say we're simplified to derivative with respect to s, and so this is just copying this. So let me just copy this here. So we can say that this is just equal to negative 100 times 25 divided by s squared. And so we'll keep that in mind as we are finding this K1 with our general equation. And so that comes from looking at this term right here. And we see we have an S100 minus 100S in the numerator, which cancel out, so we're just left with negative 100 times 25 in the numerator. Okay, so going back to our general equation then, we can say that our K sub 1 is equal to 1 over m factorial, where our m is 2. So that's an explanation mark for factorial. And then we want the second derivative, so because our m is 2 again, of s plus 5 cubed times f of s. And that's going to be evaluated at the location of our repeated roots, which is negative 5. And so, of course, I mean negative poles of our system. And so, of course, since we've already taken that first derivative, we don't necessarily need to redo that work. So we can say this is then equal to 1/2. So 2 factorial is just 2 times the derivative with respect to with respect to s of this first derivative, which we've already found. So negative 100 times 25 divided by s squared. And once we take that derivative, we're evaluating at s equals negative 5. Okay, so now it's just a matter of evaluating that. So our negative 100 times 25 is just a constant, so we can pull that out. So we have negative 100 times 25 divided by 2. And then if we take the derivative of 1 over s squared, we can think of that as s to the negative 2. So we pull the negative 2 down, and then we have s to the negative 3, or 1 over s cubed. So that is our derivative there, and we evaluate that at s equals negative 5. And doing so, we find that K1 is equal to negative 20. Okay, so we can see that was a whole lot more work than with our simple case 1 of real and distinct roots. So what we can do then, once we know all of our residues, is we can go back and we can say, well, our f of s is equal to negative 20 divided by s plus 5 minus 100 divided by s plus 5 squared minus 400 over s plus 5 cubed plus 20 divided by s. And so we can use our generalized f of t equation, and in this case, of course, our p is equal to 5. So generalized f of t equation, where our p was equal to 5, and I believe we had used a variable a in that generalized equation. And so what that gives us then is that our f of t is equal to, so we have negative 20 e to the minus 5t minus 100t e to the minus 5t minus 400 over 2 factorial t squared e to the minus 5t, all of that times u of t, and then we have plus 20 u of t for that extra 20 over s term. And so of course we could rearrange this a little bit. Oftentimes when we write polynomials, we'll have the largest t term first. We can say this is negative 200 t squared times e to the minus 5t minus 100t e to the minus 5t minus 20 e to the minus 5t plus 20, and all of that multiplied by our unit step function.